This is my version of problem number 15 from chapter 7 in the homework. It's a hypothesis test. We know the null hypothesis, the alternative hypothesis. Now please pay a careful attention to your version because your alternative hypothesis might be less than or it might be not equal to. They've also established what the alpha level is. And then they took the sample, and here is the data from their sample. We need to take that data and get it into to R. So what I'm going to do is simply copy this data, copy that data, and paste that data into R. So we've got it pasted into R. Now we need to adjust it so that it can be read by R. I need to turn this into a vector, so I'll need to use the C function, the concatenate function, and I'll need to put a comma after each one of these values. So let me pause and do that. And of course at the very end I need to put in this last parentheses, and I will store that in an object I'll call X. Now R is smart enough to know that because at the end of this line I haven't put a parentheses on the end of that I'm still meaning some more stuff. So a command can be extended over more than one line. So now I've got that value X. Let me just run that code and come down here, and so I've run the code X. I check and see what X is, and sure enough there's my data. I can double check and make sure that all of that's right. Now let's pause now for a minute and just remind ourselves what we need to do a hypothesis test. So we're talking about some distribution. It would be really nice if this distribution was normally distributed. The null hypothesis is claiming that mu, I'm going to call it mu 0 for the null hypothesis, is claiming that this is equal to, that the mean is 65.1. Now in this case we don't know what the standard deviation is of this distribution, so we're going to approximate that standard deviation with the sample standard deviation that we're getting from our sample. So we're going to take a sample, which we were just studying a minute ago, we were put it into R, and it has a certain size n. So let me go to R and just calculate what that n is. N is really going to be whatever the length of that vector x is. So let me run that code and just check down here what that is. So our n happens to be 60 in this case. So now we're going to look at another distribution. This is the distribution of sample means. One of those samples is our sample, but we're going to think about all of the samples of size 60 and find the mean of each one of those samples. So let's look at the mean of our sample. I'm going to add that to our script here, so let me get up here and we'll produce an object we'll call x bar, which is going to be the mean of x. Of course I can run that script and find out what x bar is. I'm also going to need to know S, which is going to be the standard deviation. We've already talked about that. We're going to need to know the standard deviation of our sample because we're going to estimate the population standard deviation with that particular amount. So I'd like to know where our sample fits on this, what our particular x bar is. So let me return to I'm going to run our script. The thing I'm going to try and get out of here is what x bar is. So I'm going to just run the code and just check down here what x bar is. It's 65.79. Okay, now here's some things that we know. We know that when this happens, and because of the central limit theorem, when we look at these distribution of x bars, that the mean of the distribution of the x bars, that's mu x bar, is going to be the same as the mean of the population that we selected it from. Our null hypothesis is saying that that should be 65.1. Okay, now we took a sample, and our sample came up with a value. Let me just go back and see what that value was. 65.79. So up here at 65.79 is our x bar. So the mean of the distribution of sample means is going to be the same as the population mean, and our sample came out to be 65.79. So we're going to be interested in finding the area that's above that, because we're looking at a alternative hypothesis of greater than. If your alternative hypothesis was less than, you'd be looking for the area below. If your alternative hypothesis was not equal to, then you'd be looking at a two-tailed test. So we're looking at this area that's up here. Okay. Now, some other things that we know is that the standard deviation of these sample means is going to be equal to the standard deviation of the population divided by the square root of n. Now, our problem is that we don't know what the standard deviation of the population is, so we're going to have to approximate this value by using the standard deviation of our sample divided by the square root of n. Because we're doing that, we'll need to do a t-test instead of a z-test. So let's build these things over here in R. Remember that mu sub x is really the same as the original population, so that's going to be 65.1 in our case, and that the standard deviation of the distribution of the x bars is standard deviation of x bar is going to be equal to the standard deviation of the population, but we're going to have to use S, our standard deviation of the sample, divided by the square root of n as our estimate. Now remember, we've built n up here. We looked at the length of x to make sure that we knew what n was. Okay, so I built some of the pieces there. We built this piece in R, and we built this piece in R, and we have already built x bar in R. Now we're going to find this area as a t-value, so we're going to come down here to a t-distribution, and we know that a t-distribution looks like it's going to have a t-value which is just essentially the z-value of x bar. So it's going to be x bar minus this mean divided by the standard deviation of this distribution. So it's going to be x bar minus mu of x bar divided by the best estimate that we've got for the standard deviation. And because we really didn't know the standard deviation of the original distribution, we're going to have to be using a t-test here instead of a z-test. So now we're going to want to find this area right here in a t-distribution. Okay, so we need to build that t-value. Let's do that in R right now. So we've got the pieces that we need. Our t-value is going to be, well, let's see, it was the mu sub x minus the it was x bar minus mu sub x divided by the standard deviation of the x bars, okay, which was s divided by the square root of n. Okay, so that's going to produce the t for me. Now let's look at the picture again. Shoot, I put down some things without explaining them to you. I needed to find what the standard deviation of x bar was, which is going to be s divided by the square root of n. I needed to find out what t was, which is going to be x bar minus the mu of the x bars divided by the standard deviation of the x bars. And then I needed to find the p-value, which in my case, now notice if I had just done pt, the problem there is that that would be telling me the area below t. So I'm going to, in my case, because I'm doing an upper tail test, that's going to need to be a 1 minus pt. So we can run that script and get the values that we need. We can find the t value and we can find the p value. So there's our t value right there. Copy that. And that is the test statistic. And they wanted that to 3 decimal places. So that would be 0.603. They wanted to have a p value. So there's my p-value. I'll put that in. And they wanted that to 4 decimal places. There's 1, 2, 3, 4. So that rounds to be that amount. And so now we, whoa, that's a huge p-value. It's definitely greater than alpha. So we failed to reject the null hypothesis. There is not sufficient evidence to change that. So we'll look and see how we did. And we got them all right. Okay. Your situation will be different, of course. Your p-value might say that you reject, and then you have to answer the other questions correctly. Okay. Hope that's helpful.